So let's see if there's any questions. It's 46A, 46B. All right, so if you have any questions over the next few minutes, put them in here, and we'll have a chance to go over those. So there was one question that I wanted to talk a little bit about in the homework with the 3 sorter, and whether those intervals overlap. So let me sketch that up real quick. So we have some array, and now we want to sort groups of 3. So we want to sort these 3. And so it's perfectly easy to sort 3. You just check whether the first is less than the second, and so on. So sorting 3 at a time is no rocket science. And so now the question that I believe is after this, and it confused me too the first time someone asked me this before, is, so how does it work? So if I sort these 3, and then I'll say I'll sort these 3, and then I'll sort these 3, in the way that I indicated here, it's not going to work now, is it? Because then, sure, the first 3 will be sorted, and then the next 3 will be sorted, just the 3 of them, but they have no relationship with the first 3. So these ones could be 7, 9, 11, and then the next one could be 4, 6, 8. Now, yeah, the group of 3 is sorted, but it doesn't mean that the entire array is sorted. So indeed, the trick to do the whole thing is to have them overlap. So the correct way of solving this is to sort this group of 3, and then the next group of 3 that you sort starts where the first one ends, and the one afterwards. So if we put index values here, 0, 1, 2, 3, 4. The next one then starts at 4, it goes to 6. And then the one after that starts at 6, and so on. So the key is that these intervals, they must overlap. They overlap by 1 only, but that'll be enough to eventually have the small values trickle all the way down. I'm not claiming this is a good sorting algorithm, it's just a different sorting algorithm. It turns out that it performs about as well as selection sort, but so it's nothing to write home about, but it is a sorting algorithm. So make sure that they overlap, and that should answer the question here. So, all right, I'll let you to fill in that answer. All right. Okay, now here someone else has a great question. What is the difference between an int and an integer? And so an int is a number between about minus 2 billion and 2 billion. It takes 32 bits of storage. And it's what's called a primitive type, which means that it's just stored as the value. It's not an object. An integer is an object, and so if you draw it, it's an object that contains an int. So who needs it? Why do you want to wrap an int into an object? You need it when you want to do some kind of generic programming where you deal with an array of objects, for example. And in that case, you can't put an int into an object because it's not an object, but an integer is an object, so you can. So you use an integer every time that you have an array of objects, an array list of objects, that kind of stuff. Now, Java will convert back and forth between them pretty automatically. So if you say integer n equals 3, then what you get, you'll get n to be an object reference to a blob that contains a 3. And conversely, if you now say int m equals n, then it'll take this thing out of here and move it into m, so now m will contain the number 3. So most of the time you don't really have to worry about the difference between int and integer. There's only one case where you really do need to worry, and that is when you compare them. Now, in our case, for the homework, we don't really care because we compare them with the comparator. That'll take care of it. But it might happen once in a while in your own program that you do run into this. So if you do integer a equals whatever and integer b equals whatever, and now you want to know if a and b are the same, you must use the equals method. You can't use if a equal b, because a equal b will only test whether they're the same object. They might perfectly well be different objects with the same number inside. So in this case, both a and b point to an integer object that contains the number 42, and they're different objects. And so equals will capture that. Equals will look inside and see that they both contain 42. Equal will say, well, they're at different memory locations, so they're not equal, which would be bad. So basically, you can use int and integer interchangeably, except for equality testing, where you must use the correct one. So why don't you always just use integer? The reason is efficiency. That integer needs to allocate that extra blob that contains the number. And if you don't need that, then why pay for it? You had a follow-up question? Yeah. Which one was 5b? Yeah.
You said hosts don't use recursion. Not to use recursion in it? Or is that not true?
That's true. That's true. There's no need to use recursion. I mean, the structure that I said is while not sorted, call what was it, sort 3? What was the name of the method that I made you implement? Call sort 3 on indexes 0, 2, 4, and so on, right? And so just use that pseudocode. You have a method to find out whether the array was sorted or not. That was part of what you were supposed to do for the draft. And so once you have sort 3 and once you have the is sorted, I mean, this is just a 2-minute loop. So there's no sense in messing with recursion. Yeah, so I set this one up so that if you break it into pieces, this is really a very easy assignment. To check whether an array is sorted has nothing to do with 46b, right? It's straight 46a. You go through the array and you check whether each slot is less than the one before. Right? 5 minutes. And I'm not kidding when I say 5 minutes. If you find that it takes you half an hour, that's a good indication that you need to do way more practice coding. The sort 3 thing, maybe 10 minutes because there was some slight fiddliness and you have to worry about the swapping and stuff. And now this loop is again, it's very easy. Yes?
So for one graph, you're going to go from the beginning to the end.
Yes.
It's not going to be sorted.
That's right. And you stupidly do it over and over.
So you want to come back.
you just start again at the beginning. So you call sort 3 on indexes 0, 2, 4, 6, 8, 10, and so on. And then you check, is it sorted now? And if not, you start again at 0 and do it all over. And I promise you, if you do it often enough, it will sort the array. And the rationale for why it does sort the array is that in each of these individual intervals, so you have this intervals that's 3 long, right? And after the first step, the smallest one gets here. So you have small, medium, large in here. Well, the next time around that you look at this one before, because remember they overlap, if this small was smaller than the other ones that came before, then it'll eventually percolate down here. And eventually, the smallest one will go all the way in the bottom. It might take a while, but what do you care? So each time, the smallest one will percolate a little bit down, 2 steps, and eventually it must hit bottom. So if you want to see what it looks like, you can simply print out the intermediate arrays in your solution and take that code out before you turn it in, but print it out and you'll see how the thing slowly gets how the small value slowly gets towards the left. Yeah?
So you said we don't need to use the recursion?
There's no advantage to using recursion because I gave you a perfectly easy loop. You already had to implement the isSorted method anyway. It's part of the draft. You already had to implement sort 3. And now all you have to do is write a 2-line loop. The loop that you see here. So there's no advantage in using recursion. But if you want to get some intuition as to why it works, go ahead and add a 3rd line to the loop that just prints out the current value of the array, and then you'll see the values slowly meandering down. It's not a great sorting algorithm, but it does sort. So as becomes apparent to you now, there's all sorts of different sorting algorithms with different performance. I'll give you a really bad sorting algorithm. Pick a random permutation and apply it to the elements, check whether it's sorted, and repeat. Eventually, you'll have to hit upon the right permutation. It just might take a very long time. So that would be a very bad sorting algorithm. All right. Other questions? Oh, there was one other thing that, gosh, if I could find that, that I wanted to call out. No. Okay, I can find it right now. But someone had some question about something that NetBrat did, and a student, bless her heart, gave his answer and said, you'd be better off writing your own tester. And amen to that. It really is your job to test your own code, and if you find that the NetBrat tester is confusing or not good enough, and in most cases it will be confusing or not good enough, go ahead and write your own tester. NetBrat is just there to help you out. It's not there to do the work for you. So if you find that the tester that's there that you don't quite know what's inside it, it just randomly fails, you stare at your code, you don't quite know what it does, the best thing you can do is to write your own tester. In real life, that's of course what you expected to do anyway, right? No one is going to pay you for writing a bunch of code that passes some tester that they already have. People are paying you for developing and testing your own code. So by all means, go ahead and write your own testers. And as we'll see in the lab today, when we talk about test-driven development, it's just something that every professional does all the time. All right, well, let me go on with the lecture, and then I'll have another sweep at the questions. Oh, here. Oops. Did I not update the lab? Okay, it's lecture 11. Whoops. What happened? Huh? What the? Oh dear. Oh, I see. Spring 2012. Okay, well, for whatever reason. So, so we're going to talk about merge sort, and so merge sort is kind of actually is something that I'm sure you've seen before in your life. And just think about if you have some kind of sorting task where for whatever reason you have a pile of magazines or something that you need to sort chronologically, and so you have this big old pile, and you happen to have a friend with you, and what do? You cut the pile in half, you sort half of it, your friends sort half of it, and then you merge them together. I don't know if you've done this, but I've certainly done that in the olden days when I had to grade paper exams. I'd get together with my friend, and he'd total up half of them, I'd total up the other half, we'd sort them, and we merge them back together. So that sounds like a good idea to divide the labor when you have two people, but it also turns out, maybe surprisingly, that it's has a much better performance. So here's an example. So we cut an array in half. So we have an original array here, we have this other array here. We sort each half. Now you might say, how are we going to sort each half? But that's where we're going to be using the miracle of recursion. It's a smaller array, so we figure that somehow we'll be able to sort it. Recursion means that you can deal with smaller problems. So I have an array with 10 elements. I cut it into two arrays of 5. By a miracle, the shorter ones can be sorted, so I just sort them, and now I need to merge the results back together. Now, the merging is a little bit fiddly, so let's have a look at how one does this. So what you need to do for merging is you have to have an index in the first and in the second array after they've been sorted. And now you compare and you see how the one in the second array is smaller, so you move that one into the final array. You need a third index for the target position. And now after each step, you increment the target because you've just filled it, and now on the source you have to figure out which one did you just copy. Oh, it was the one on the right, so increment the second one here. You leave the first index the same. So now we're comparing the 5 and the 8. And so we move the 5, that's over here. We increment the target. We always increment the target. And here we increment the first source, which now is at the 9. Now we compare the 8 and the 9. Now the 8 wins out, so we copy the 8. We increment the target. And now we increment over here where it points to the 11. So you always figure out from which of the two halves do you take it, and you move that one up. Let's have a quick look at the source code for that. Come on. Ah. So we're looking at this merge procedure here. Here you see the indexes I first, that's the index into the first array, I second, that went into the second array, and j, that's in the target. And so we're checking whether the first half is less than the second half, and if so, we copy it across and increment the first index. Otherwise, we copy it from the second and increment the second index, and in either of the two cases, we increment the target index. All right, so after having done that, there is a nasty bit of a complication, because it could happen that that when you do the merging, you run out of stuff. This is not actually a very good example of that, but let me show you another example that makes that more dramatic. So let's say I have an array 1, 2, 3, 4, 8, and I merge that with 0, 9, 11, 12, 13. So I first pick the 0, and then over here I pick the 1. And now if you look at, now I'm going to have to pick all of the 1, 2, 3, 4, 8, because they're all smaller than the 9, and I have run out of space. I've run out of elements to take from the first array. Now at that point, once I've run out of elements to take in the first array, then I switch strategies, and then I say, okay, now just copy all of that stuff. So you keep on merging while you have stuff in both of the arrays and you can compare them. But once you run out of room in one of the arrays, once you've taken everything from it, then you say, oh, now I'm no longer going to compare. I'm just going to copy the remainder from the other array. So in source code, that looks like this. So while there's still stuff left in the first array, just go ahead and copy it. And while there's still stuff left in the second array, go ahead and copy that. Notice that in these steps here, I always increment both the index into the first array and the target index, and over in this loop I increment these ones here. All right, so that should bring me up to my first clicker question. So go ahead and pull that method if you haven't already looked at it. It's in the source code that comes with the book. It's in the merge sorter class. Look at those two loops. And so my question is, see, there's actually 3 loops here. Sorry, not 2 loops, 3 loops. There's this loop here. There's this loop here. And then there's the one over here. And my question is about what is true after the first of those 3 loops is finished. So what is true right here, where the red cursor is? You need to open up your laptop and look at the code. Oh, so look at the merge method. So here's the merge method. The merge method has 3 loops. First loop, second loop, third loop. And so my question is, after the first loop, all right, so the majority answer is is 3. And that is in fact true because we don't really know which of them get added first. It could be that most of the elements in A are small or most of them are big. We really have no good way of knowing that. It could, because they're independent of each other, right? We had an unsorted array, we cut it in half, we don't know what's in the left or in the right, and what we do know is that we ran out of room in one of them. So let's look at the loop condition carefully here. So that we're staying in the loop while there's more stuff in the first array and there's more stuff in the second array. We exit the loop if we're done with the first array or we're done with the second array, and that's answer 3. All right, so notice that those other 2 loops here, this one and this one here, only one of the 2 will actually execute. So one of them is a waste and the other one will execute. It's just we don't know which one is a waste, so we have to put them both. All right, so next question here is, now how long does the merging actually take? All right, so let's let's figure it out. And so what we need to find out is how many elements are visited in this process. So at each, and let's for simplicity assume that we're just going to be running through the first loop. So we'll assume that each of the halves have some mixture of small and large elements, and they're all nicely distributed. So every time that I make a comparison, I look at an element here, and I look at an element here. That's 2 visits. And then I move it over here. That's 3 visits. And afterwards, I increment some indexes. What do I increment? I increment either the one on the left or on the right, depending on which one I took. And I increment the one at the bottom, and then I repeat the process. How often do I repeat the process? It's easiest to look at the target that I need to fill up. This thing has n slots. I repeat this process n times. So n times, I have 3 visits. Now, what about those cases where I'm done early with one of them and I just need to copy the other? Well, so let's say that I'm done with all of this array here, and now I need to just copy, say, this tail end here. Well, each copying takes only 2 visits, because I only need to look at this one and this one. I don't need to compare anymore. Well, 2 visits is better than 3, so in the worst case, I could say, the 3 visits will cover it, and so I can say it's O of n times 3, and that's the same thing as O of n, because the 3 doesn't count. And so intuitively, we're making a visit through this entire array here, looking at everything once, and then we at the same time look at the ones up here, but there's no secondary loops involved. So it's a single loop that does this. So let's see how people did. And people did great. So All right. So now, when you run merge sort, then the numbers are very promising. So on the left you see merge sort in milliseconds. On the right you see selection sort in milliseconds. And you can see that merge sort is much, 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 much better. Right? It's 205 milliseconds. That's less than a second versus almost 20 seconds for selection sort. And as we've seen last time, when we sort like 1 million of them, it may take several hours with selection sort. With merge sort, it's still going to be in the seconds. And so when you plot it, again, you see there's no contest. So that the selection sort, you have this parabola here going way up, quadratic growth. And merge sort, they're so good that I can barely draw the thing. I mean, it just looks like basically a flat line. So let's see why that is so. So we need to ask ourselves, how often is an array element visited? And for simplicity, we're going to assume that n is a power of 2, because we keep cutting the thing into pieces, and that is easiest when you have a power of 2. The same analysis holds otherwise as well, but it just gets a little messier, and I want to spare you the math. So, think of n as 1024, for example. So we have these two subarrays, and now we merge them together. And now there's a little bit of trickiness here that we hadn't paid attention to before. This 3 visits to merge each element, that's what we just did in the exercise. Now, when you make these subarrays, unfortunately, you need to copy stuff into them. So you have this big array, and you can't sort in place. It's not like selection sort, where you can just leave the things in the original array. You have to come up with 2 new arrays that you then sort recursively, and that copying costs a bit of money. So here I have my big array, and I did need to actually make these 2 ones and copy these over. Then I sorted these, and then I merged them back, and then they can go away again. But I did need to pay for this, so it's not free. So the total of 5n visits for that work. So now I need to deal with the recursion. So if it costs me n visits, or t of n, then the total visits now is, here's my 5n, that's for the copying and the merging. And then for the recursion, I do need to pay for the left and the right. That's t of n over 2, and another t of n over 2, right? This thing costs t of n total. This one is half the size, so it costs t of n over 2. Now, or if I simplify it, t of n is 2 times t of n over 2 plus 5n. Now let's do this one more time. Let's figure out what's t of n over 2. Well, I have a formula for this, and I can use it again. So let me rewrite this formula here so that the n's aren't so confusing. I'll just rename it to k. I did nothing but change n to k. And now I can plug in, if k is n equals 2, n over 2, then I get t of n over 2 is 2t of n over 4 plus 5n over 2. That's what I have here. Now when I do that again, I get the formula here. And when I plug it back in, then you see that the factors of 2, they start accumulating here. And over here I'm now down to t of n over 8, and I have a bunch of these 5n's that appear at every step. When I keep on going it, well, I can only do it some number of times until I'm down at an array of size 1, at which case I don't have any more work to do. And so when I repeat it to the case that if n equals 2 to the k, then I'll stop and I have this total cost. So if n is 2 to the m as a power of as a power, then I get that t of n is 2 to the m, t of n over 2 to the m, which is t of 1. Yes, yeah, t of 1 plus 5 nm. Okay, now I have this pesky m in here, but since n is 2 to the m, I can solve for the m by taking the log on both sides. and then the log of base 2, and then I get on the left-hand side log 2 of n, and on the right-hand side I get the log 2 of 2 to the m, which is m. And that way I can eliminate the m. And I get that t of n is n plus 5n log 2 of n. Now, to turn this into a big O expression, we can drop that n term. So because we had an n plus n times log of n, so the lower order n can go. That was a factor of 5 we don't care about. You may know from middle school that any two logs are related by a constant factor. So log 2 of n and log 10 of n grow the same way. They're like log 10 is 3.5 times as log 2 about. So you can omit the factor. But if you don't like it, just think of it as log 2 all throughout. So the big O notation is O of n log n. And so it's kind of this miracle that's been happening. It's not quite clear why. Why should this be better than O of n squared? Remember, for selection sort, we had O of n squared, and now all of a sudden we get O of n times log n, and it obviously is better. So compared with O of n times n. The n is the same. And then the question is log n better than n? Is it much better? Is it a little bit better? Well, to see how much better it is, take some large number, like 1,000,000. What is log 2 of 1,000,000? All right, let me ask something easier. What is log 2 of 1,000? Log 2. All right, let me ask something even easier. What is log 2 of 1,024? Well, let me ask something that's even easier. What is log 2 of 2 to the 10? 10. All right, that's what the log is. 2 to the 10 is the same thing as 1,024. So the log 2 of 1,024 is about 10. It takes 10 powers of 2 to get up to 1,000, and a little bit extra. So log 2 of 1,000 is about 10. Log 2 of 1,000,000 is what? So you multiply 10 2's and you get 1,000. How many 2's do you multiply up to get 1,000,000? Ten of them give you 1,000, and change. How many of them do you need? How many 2's do you need to multiply up to get 1,000,000? Yes, sir. 20. Right? Because now you just do it again, and take another 10. That gives you another 1,000. And 1,000 times 1,000 is 1,000,000. So, if n is 1,000,000, then log n is 20. Ladies and gentlemen, I put it to you that 20 is better than 1,000,000. Much better. If n is 1,000,000,000, then log n is 30. If n is 1,000,000,000, then log n is 40. Log n is pretty darn good if you can get it. So, of course, it's not quite as good because the sorting is still n times log n. So if you have 1,000,000,000,000 records, you still pay for the 1,000,000,000 times 40, but that's a lot better than 1,000,000,000 times 1,000,000,000. And so that's why the sorting with merge sort works so much better. So it's just this miraculous thing that if you do the laziest possible sort, where you say, I have my data set, I'm going to cut it in half, I'm going to have someone else sort the two pieces, and all that I'm going to do is merge them together. That laziest possible approach is actually a much better approach than what we had before, where we said, let's find the smallest one, let's find the next smallest one, let's find the next smallest one. So by the miracle of recursion, that you say, let someone else worry about sorting those pieces, it turns out that not much work needs to be done in the end. So it really is somewhat miraculous. And there you go. So, all right. So, one more question to make sure that everyone can think about these numbers. And then we'll go to the lab. It takes 10,000 times as long let's make a choice number 4. Surprising how many people picked number 3 already. Okay, how the heck do I edit this? Edit here. Come on. Improve this question. Oh, look at that. All right. Now there is. 10,000 times as well. All right, so let's think through this. With selection sort and merge sort, the longer array takes 1,000 times as long as with the original array. That can't be right, because last time we learned that when you use selection sort and you increase the size by some factor, that the time grows by the square of that. So we know that with an O of n squared algorithm, if you multiply the size by 1,000, the time must go up by 1,000,000. So this can't be right. Now with selection sort and merge sort, the long array takes 1,000,000. For selection sort, that's certainly true, but for merge sort, it should be less than that, right? Because somewhere our log goes in. Now with selection sort, the longer array takes 1,000,000 times as long. That's true, we know that. With merge sort, it takes about the same time as the original array. Now that sounds tempting, but it can't be quite right. And that's why I drew the little picture here. So I have my original array with n elements, little thing, and now I have one that's much larger. It's got to take at least 1,000 times longer to sort the bigger one, because someone has to look at those elements at least once. You can't sort what you don't see, and just looking at the elements of a much longer array is going to have to take a substantial amount longer. So let's see what the last option says. So here we again have the 1,000,000 for a selection sort, and now it says it takes about 10,000 times as long. Well, why 10,000 and not 1,000? I guess that's where the log n comes in. So we're going to choose 4, and saying that the 1,000 would be the n and the 10 would come from the log n, and that seems the most plausible answer. And let's see. Doing. And so that was the majority answer. So I guess C got some early votes because D wasn't available yet. All right. So I really quickly want to go over quicksort because it is going to be a part of the next homework assignment. Yeah, that way you can get a head start of it. Quicksort is superficially similar to merge sort, but it uses a different way of doing the divide and conquer. So with merge sort, we took our array and we cut it in half, and then we sorted each of them separately. And quicksort does it in a way that they think is maybe a little cleverer. They say, let's look at the first element in the array. That would be, well, it doesn't actually matter which element we take. Let's take an element, and in this case we're going to take the 5 and make it so that that every thing that's smaller than the 5 we move to the left half, or to one array on the left, and everything that's larger we move to the right. So here you find everything that's smaller than 5, and over here you find everything that's larger than 5. Now that costs, and how much does it cost? It's a linear traversal through the array. For every one of these elements we need to see, is it smaller or is it larger? And then we copy it to one half or the other, so that costs a little bit again. All right, so we've done that. Now I can recursively sort the left half, and I can recursively sort the right half. They're smaller arrays, so I should be able to recursively do the same thing. Now the beauty is I can do that in place. I don't have to come up with new arrays. I don't have to do any copying. And now comes the real beauty. I've sorted the left half, and I've sorted the right half, and now what do I need to do? Nothing. I am done. Why? because all of these elements were less than 5. All of these were greater or equal than 5. The left half has been sorted recursively somehow. The right half has been sorted. So the whole thing must be sorted. So that's a beautiful algorithm. It's very simple. It says pick an element, it's called the pivot. Move everything that's less than the pivot to the left, move everything that's greater than the pivot to the right, recursively sort. And you're done. As beautiful as it is, it actually does not perform as well as merge sort. There's some situations where the distribution into the left and the right is unfortunate. Over here, it looks like it would fall kind of somewhat symmetrical, but there are always some situations where the left gets real big and the right gets real small, and then you don't get that logarithmic cut down that you get with merge sort. So in practice, it works well for random data sets, but it doesn't work as well for arbitrary data sets. So we're not really going to consider it as much. All right, so you have it. You have here the basic idea. Look for it's going to come up in the next homework where you're supposed to make a slight modification of this thing. All right. Oh, there's one thing that I guess I should talk about because it's going to hit you in the homework, and that's how to do the partitioning. I said move everything that's left to the less than the pivot to the left, and move everything otherwise to the right. And so it turns out that's pretty easy to do if you look at the work as you're working through this thing. So you have your pivot somewhere, that was the value 5 in my example, and everything that's less or equal 5 you want here, and you want values that are greater or equal 5 over here. And now you have this area that's not yet analyzed. So now you're going to look at this value, and you're going to look at this value. And there's a few possible situations. Maybe this thing here is less than 5. You just extend this area. Maybe this value here is greater than 5. In that case, we'll come to that in a minute. Maybe this value here is greater than 5. In that case, you just extend the area to the right. And now comes the worst case. Maybe this thing here is greater than 5, and maybe this thing is less than 5. And then you just swap the two, and you're also good. So that's something that you're going to have to think through in your own head, and you will when it comes to the homework, because you're going to have to modify that algorithm slightly for the homework. All right. That's what I wanted to say about that. Moving on to the lab. I am still baffled by why that doesn't show up. Oh, because I'm... Okay, we're going to be moving on to lab 4. Let's hope it's here. Okay, I'm going to get it locally, and it will be here in just a minute. All right, lab 4 is going to ask you to learn about JUnit, which is a more powerful way of doing unit testing than the puny little NetBrat thing that we've been using so far. It's going to go back to the good old lab 2, the one with the directory, and if you can unearth your code from that, by all means continue with it. Otherwise, I'll just give you the starter code that you can use. All right, so let's get going with it. We won't get done with this today, but my hope is that we're going to get somewhere into step 3, C. So do as much as you can, and we'll see how long it takes you. Now let me just make sure that you can actually access it.